Welcome back to my YouTube channel, everybody. Chapter 1, Lesson 1 is on functions, and we're going to start to define a function and then eventually get into characteristics of a function. So to do this, let's first talk about some sets of numbers. So we have different sets of numbers, and if you look at this chart, we have rational numbers and irrational numbers. Rational numbers are numbers that can be written as a fraction. Irrational numbers are numbers that cannot be written as a fraction. And then we have integers, whole numbers, and naturals. And those are really similar to each other. Integers can be positive or negative. There's no decimals, no fractions. Whole numbers are only positive and zero numbers that are not decimals and fractions. And then naturals are just the positive counting numbers, so 1, 2, 3, 4, and up. And if you take a look at this diagram over here, this shows like a Venn diagram and how some of those sets are subsets of other sets. As an example, the naturals is a subset of the whole numbers because they're pretty much the same except for the whole numbers includes the number 0. The whole numbers are a subset of integers, and the integers are a subset of the rational numbers. However, the irrational numbers are not a subset of anything, but all of these numbers are considered to be a real number. And real numbers are numbers that you can place on a number line. So the first thing I want to go through is set builder notation. Here's an example of set builder notation. You've got 3 different parts to it: the green part, the red, and then the blue. And so the green part, it just describes the variable that you're using. Typically it's an x, but it doesn't have to be an x. The red part gives a certain description of the set, and then the blue just gives a little bit more detail on the different type or different set of numbers that you're working with. So here's an example 1. It says use set builder notation to describe this set. And if I was going to do part A, I would say all numbers x such that x is greater than or equal to 8, and x is an element of, this would be the integers. So this is set builder notation. Again, there's 3 parts to it. If you go into part B, all numbers less than 7, so like we would include 6, 5, 4, 3, all those numbers, but also decimals and fractions and whole numbers. And so to write this in set builder notation, we'd say all numbers x such that x is less than 7. And then for this, we'd say that x is an element of the real number system because we're including decimals and fractions and whole numbers, everything that is less than 7. 2 more examples of writing in set builder notation. You can see the next set, 1a, we'd have all numbers x such that x is greater than or equal to 1, and x is an element of, this would be natural numbers. And then the last example here, 1b, again we'd say all numbers x such that x is less than or equal to -3, and x is an element of the real number system. So those are 4 examples of writing a different set in what's called set builder notation. We're also going to talk about writing, whoops, what just happened there? We're also going to talk about writing numbers in sets in what's called interval notation. So interval notation, we use brackets and parentheses, and sometimes we use infinities and sometimes we use negative infinities. And you started using this in Algebra 2, and we'll continue to use it this year in Advanced Math. So example 2, we're going to write this set using interval notation. So all numbers greater than -8 but less than or equal to 16, we would write like that. The parenthesis means greater than, and the bracket means less than or equal to. Letter B, now if we have all numbers less than 11, we'd have to go from -infinity to +11. We need to have a parenthesis on the 11. So that's how you indicate all numbers less than 11. With interval notation, you always write smallest to biggest, working left to right. Okay. Example C here, we've got 2 different sets. We've got x less than or equal to -16, and we also have x is greater than 5. So we're going to have to use a union on this. All numbers less than negative 16 or equal to it would look like that, unioned with all numbers greater than 5. So we have two separate regions to satisfy this set of numbers. 3 more examples of the same type of problem, writing in interval notation. So if it's greater than or equal to negative 4, but less than negative 1, we would need a bracket on the negative 4 and a parenthesis on the negative 1. Again, working smaller to bigger, left to right. Example 2b, all numbers greater than or equal to negative 3. I would need to have a bracket on the negative 3, and it would go to infinity. And then lastly, example 2c, all numbers greater than 9 or numbers less than negative 2. So there's the numbers that are less than negative 2. We would union that with all numbers greater than 9. And that's what your interval notation would look like for example 2c. So now I want to get into what a function is. Before we get into what a function is, remember that a relation or a relationship is a rule that pairs an element with set A to an element in set B. Now we call the set of inputs, we call that the domain. And we call the set of outputs, we call that the range. So our formal definition of a function is for every element in the domain, there exists exactly one element in the range. So let's go back and look at this example from the first slide that I had. If you read this with me, it says many events that occur in everyday life involve two related quantities. For example, to operate a vending machine, you insert money and make a selection. The machine gives you the selection item and any change due. Once your selection is made, the amount of change you receive depends on the amount of money you put into the machine. So that's a good example of having inputs and outputs, and that is similar to representing a function. The inputs is the different type of money that you can put into the machine. The outputs would be the different items that you can select from the vending machine. So we're going to have functions represented 4 different ways. Number 1, verbally. You're going to be given a sentence. And here's an example of that. The output value is 2 more than the input value. So that's just a relationship. As an example, 5, 7. Oops, yeah, 5, 7. 10, 12. There'd be lots of coordinate points that we would satisfy that particular function. We also are going to represent a function numerically, just with values. Now this is just listed as coordinate points, but they could be listed in an XY table. I'll show you some examples in just a second. We can also have a function represented graphically with obviously a graph with either points or a curve. And then number 4, algebraically, sometimes you'll be given an equation and asked to identify if it is a function. So here are some examples. First of all, this is a mapping. And so you can see the set A represents the domain, and we've got 4 different values in our domain, 1, 2, 3, and 4. And the set B represents our range. And even though there's 2 different elements in the domain that map to the same output, this still represents a function. Because if I say, what's the output when the input is 2, your answer would be 8. And if I say, what is the output when the input is 3, again, your answer is 8. Those are the only correct answers for the outputs when I give you the inputs that I gave. So this does represent a function. However, if you look at this XY table, this XY table does not represent a function because for the X value of 3, what is the output? Well, you can't give me 2 different outputs like 4 and -1 like you can see in this table. Thus, this is not a function because for the given input of 3, there are 2 separate outputs. Also, with a graph, we have something called a vertical line test. If you place a vertical line anywhere on the graph, it cannot cross the graph more than once. If it does, it fails the vertical line test and it's not a function. So let's do some examples. Example 3, determine whether each relation represents y as a function of x. So the input value x is a student's ID number, and the output value is the student's score on a physics exam. So if I enter a student's ID number, how many different scores should come up on for their physics exam? Only 1. So this does represent a function because if I type in a certain ID, I should be given only one score that they got on the physics exam. Go to example 3, part B. If you look at this XY table, you're going to look at all the X values. Since all these X values are different, this does represent a function. It doesn't matter that 0 and 6, those input values both produce the same output. That doesn't matter. Part C, we have a graph of a sideways parabola. As you can see, if you place a vertical line on this sideways parabola, it's going to cross the graph more than once. Therefore, it fails the vertical line test, and this is not a function. And if we're given an equation like this, well, obviously, this has a y squared in it. If it had an x squared, it would be a u-shaped parabola curve that would open up or down. Since it has a y squared, it's going to have a u-shaped parabola curve opening left or right, and so that's going to fail the vertical line test, and this is not a function. Another good example of that is, let's put an input value of, let's just say 2. What's the output going to be? So as I continue to work the problem, you can see that we get y squared equals 9. And so if we square up both sides, that would give us y equals plus or minus 3. And so what that means is for the input value of 2, you get 2 separate outputs, thus this is not a function. More examples of the same. 3a says the input value x is the area code, and the output value y is the phone number in that area code. So like if I tell you that the area code is, oops, let's erase that. If I tell you the area code is 320, does that determine that the phone number is going to be 7962410? Or is it possible that there's other phone numbers that exist for the area code of 320? Well, certainly, given the area code, it's not going to determine what the phone number is, so this is not a function. Looking at letter 3b. Looking at this table, this is not a function because for the given x value of 5, there are 2 separate outputs, 8 and 9. Example 3c, if you place a vertical line anywhere on this graph and then take that line and slide it left to right, like I'm doing now, I know my line's not perfectly straight, but if I slide that line left to right, I never cross the graph more than once. Therefore, it does pass the vertical line test, and it is a function. And then example 3d, we have an equation, and that equation, if you got y by itself, it would look something like this. Negative 2x plus 6, that would produce a line, and every linear function is a function. So this one does represent a function. For any input x, there's exactly one output, the y. So that is everything for day 1 of lesson 1.